Alex presented the low-level view of speculation and so on. I will actually present what that means for the users and why it's a bit of a pain for the users, even if you have all your mitigations set up in the kernel. I will talk about CPU models, which are already a tricky topic in and of themselves in QEMU and libvirt, and a little bit in higher levels, such as overt or OpenStack. So let's start taking a step back, and if somebody asks you this question, can this OS run on that machine? The answer is almost always going to be, it depends. Depends on what? Depends on many things, actually. Depends on the host processor, depends on the microcode version, depends on the kernel version, depends on the QEMU version, and even if everything is the same, it depends basically on the command line, including the machine type. Why? For example, you could upgrade microcode, and then a CPU ID flag suddenly disappears, which is what happened a few years ago for TSX. You could also be downgrading microcode because there was a bug in the older Microsoft, and the CPU ID flag disappears. And that's what happened this year. The first round of updates had the IBRS flags to mitigate Spectre v2. The second round of updates consisted basically in removing the microcode, because it was buggy on some processors. Another possibility is that you upgrade QEMU, a new kernel is required. The new kernel, for example, QEMU adds support for KVM PVOI by default, and that requires Linux 3.6. And this new kernel is newer than what you have in your machine, and your machine doesn't have the KVM PVOI flag, and QEMU complains and doesn't start your virtual machine. It's also possible that somebody has changed the kernel module parameter and the flag has disappeared. For example, somebody had enabled nested virtualization by default, then they reinstalled the machine, they forgot to re-enable it by default, and your virtual machine is expecting VMX CPU flag. It's not there, and the virtual machine doesn't start. And also there can be more interesting cases. Like you migrate to an older kernel, vhost drops support from some virt.io feature, and the live migration fails. In this case, it's probably unlikely that the machine would fail to start, but it may fail to migrate, for example. So how do we deal with this? Basically, at the lower levels of the stack, there's nothing you can do. They are the ones that decide whether the features are available. If the processor doesn't provide, I don't know, let's keep the same example as before, nested virtualization. Sorry, if the hypervisor doesn't provide nested virtualization, there's nothing that QEMU, libvirt, OpenStack, or overt can do about it. If the processor doesn't support AVX512, there's nothing that KVM, QEMU, libvirt, overt, and OpenStack can provide. So basically, the lower levels are the ones that are the bosses and decide whether a feature is available or not. On the other hand, the lower levels of the stack can also be told which features to enable. So if you know that you're running on a new machine, but you might want to migrate to an older machine, QEMU and libvirt can turn off some features at the KVM level. The VM doesn't know that that feature exists, and then you can migrate to the older machine because that feature won't be in use. And that's the case for CPU models and why we have them. Basically, it's a matter of guest ABI. Across live migration, you cannot change the guest ABI. You cannot change the family model stepping. You cannot change the flags that are there, and so on. In general, live migration should be completely transparent to the guest. And what the CPU models do is to describe the ABI of the guest processor. And this lets you do two things. Set up identical ABIs on source and destination independent of what is in the actual processor that you're running on. And also, thanks to knowing the CPU models in advance, you can find out which hosts can be started, can be a place for your VM. So like this machine wants AVX 512, this host doesn't have AVX 512, sorry, find another host to start it. A SPU model basically consists on family model and stepping, which has more or less arbitrary numbers. This one comes from my laptop. They can be found in POC CPU info if you're curious. And also they consist of a model name, such as, in this case, 7th generation Core i7. This family model and stepping and model name, this can be confusing to people that have never used virtualization. They are not necessarily the name and family model stepping of the processor that you're running on. So some programs actually do look at family model and stepping in order to choose, for example, some microarchitecture dependent optimizations. For example, they know exactly what the execution units are in a Skylake, and they write their code so that it fills those execution units nicely. For example, a program that actually likes, a library that actually likes to look at family model and stepping is GMP, the multi-precision numbers library, which means that you probably won't have the best performance from GMP if you're running with a CPU model other than the one you actually have in your computer. But basically, it's a necessary evil to avoid performance. What programs should never do is use the family model stepping to decide whether something is there. That's evil, don't do it, because what you have for that is hopefully, usually, CPU flags, CID flags. There's dozens of them. This is just the first 1.5 lines, basically. And most of them are really there in all machines nowadays, but still the new ones, they're every generation of the Intel or AMD processors had a few of them. We keep them updated in KVM, in QEMU, in libvirt, and everywhere. So you can actually pass all the feature of the processor to the guest, and the guest will look at the flags and use them if he likes to. CPU models in QEMU and in the future also CPU models may contain MSR values. So some MSRs contain things that are very similar to CID flags, but for whatever reason Intel decided to put them in an MSR rather than CID flag. One example is the VMX capabilities. They are not in CID, you can find them in MSRs. And when we will enable nested virtualization live migration, we will also add to the CPU model. The CPU model Skylake has this, and this VMX feature. NehalM has these others, and so on. And these are MSR values, but they also are part of the CPU model. So CPU models in QEMU come in two different flavors. Either named configurations. These are designed to allow the most flexibility in scheduling your VMs on your hosts. And in turn, they could be named after processor code names, minus CPU Ivy Bridge, for example. They can just be the least common denominator. So for example, minus CPU KVM64 is basically the oldest CPU that could run a 64-bit KVM hypervisor. And so if you are running KVM, you must have those features, because otherwise you wouldn't be able to run a hypervisor in the first place. And also there's another one, that's another group, that's QEMU 32 and QEMU 64. They were added in 2009. TCG provided those features in 2009. That's what is part of QEMU 64 nowadays in 2018. Of course, as you can see in the last line, because I knew you have already read it, it's the default. And so the worst one is the default. Other architectures actually have a better default, which is to do pass-through configuration. Pass-through configurations are simple. They usually perform well. You can choose whether to only include features that QEMU knows about, minus CPU host. And in that case, you can do live migration to an identical virtual machine, to an identical physical machine, sorry. Or you can choose to enable blindly all the features that KVM implements. In that case, no live migration is possible, because you don't know how to migrate the state for those features, if any. And that's why the way to do it is minus CPU host, comma, migratable equal off. So why is QEMU 64 so horrible? Because it hasn't updated for 9 years now, for example, it's vulnerable to those speculative execution vulnerabilities that require adding a CID flag for mitigation. In this case, if you start a virtual machine with -CPU QEMU 64, then you go to sysdevices, system CPU vulnerabilities, and you find that it's vulnerable to speculative store bypass, which is the one that came out around May, just to put a timeline. Libvirt is similar with one interesting difference. You can do name plus flags just like QEMU. You can do host pass-through, which is basically same as CPU host with the default migratable equal on option. In that case, you can do live migration across machines that are identical in processor, kernel, and microcode. But libvirt has also one advantage. Libvirt has some extra information that is stored in the libvirt daemon and transferred to the destination machine before live migration start. And for this reason, libvirt can use something called the host model, CPU model. It's converted automatically to a name and flags combination when you start the VM. And this name and flags combination is transferred to the destination of the live migration without you noticing. So basically what happens is that the destination libvirt knows the name and flags, and so it can allow live migration from an older host to a newer host. For example, I don't know, a Westmere to a Skylake or an Ivy Bridge to a Skylake. Live migration from new to old host will fail gracefully because the destination host will find that something is missing and will not allow the live migration to continue. The only restriction, apart from having to do live migration one way, is that if a flag is not known to any of KVM, QEMU, or libvirt, this automatic conversion to name plus flags is impossible, and so host model will be restricted to something like the default -CPU host, with additional restriction that the flag has to be known by libvirt, not just by KVM and QEMU. A host model is a perfectly fine default in most cases. It used to be buggy, but now it's fixed. So, for example, that's the default that Red Hat uses for OpenStack. So Spectre and Meltdown, let's go to the topic of this talk. So Spectre and Meltdown has various ways to report what's going on with these vulnerabilities and the availability of mitigations. CPU ID bits, MSR bits. There's also Chickenbit. How many of you know what a Chickenbit is? Okay, so a Chickenbit, it was mentioned also before in the previous talk, is basically a bit that the processor vendor usually don't tell you about, but everybody knows that it's there. And it disables processor features randomly, like so that if they find that there is a bug, they can disable it in the firmware usually, and your processor will probably run a bit slower or very slower if you end up disabling the whole TLB, as it happened a few years ago. So processor bugs are not new. It's just that these ones are more painful because they are applied to every computer in existence or close to. But Chickenbits existed before for other processor bugs. They still exist. And they are a bit of a problem because the availability of Chickenbits is very, very, very processor dependent. And usually the only way to know that it's there is to look at the family model and stepping. As I said before, the family model and stepping has no bearing in a virtual machine to what actually is the FMS in the host. Another unexpected problem, which is not a processor issue, it's a virtualization issue, is that previously you had some features that nobody used, and suddenly they become super important for performance. Without PCID, for example, the Meltdown fix imposes a TLB flash going to the kernel and another going back to user space. So things can be really slow. And so let's look at these one by one. So the CPUID bits. And the dilemma is whether to add new models in QEMU and libvirt or require the user to add the flags manually. The first time through, we did add the new models because we sort of understood that there would be other problems, but we didn't know how bad it was actually, and also there wasn't really time to support flags through the entire stack, especially in OpenStack and OVirt. So adding new models, we did it for Spectre v2, but it doesn't scale. And now we have SSBD, PCID, spec control, virt SSBD, AMD SSBD, MD no SSB, IBPB, and probably others that I forgot. And OpenStack caved in and now supports adding the flags. As of January 2008, when the first wave of bugs came out, it didn't, but now it does. So after Spectre v2, we are not adding more models. A curious thing is that in the beginning, OpenStack was saying, yeah, we'll backport this feature of adding new CPU flags to the old versions, but we will only support PCID because it's the only one that matters. Sure. Look there. So again, if you use a host model, it's much better for you because all the critical flags will be added automatically, provided that you update microcode, Linux with KVM, QEMU, and libvirt, which you should anyway. So what about MSR bits? MSR bits, before we added support for them, they couldn't be probed by QEMU because reading the MSRs is a privileged operation. There's no distinction between MSRs that user space can just read and MSRs that are off limits for user space. And in any case, the fact that an MSR feature is available on a host doesn't mean that it's supported by KVM. So anyway, KVM has to mediate between the host value and the MSR of the MSR and the values that it wants to communicate to QEMU. So in order to do this, we added two new ioctls to KVM. It's called KVM get MSR feature index list, and the other is called KVM get MSR. KVM get MSR already existed on the vCPU file descriptor. Now we added it also to the system dev KVM file descriptor. And these KVM ioctls were on the to-do list even before Spectre and Meltdown. We finally implemented them because we had a very good reason, but they're already used for a lot more stuff. For example, QEMU can decide to pass through the microcode revision if it wishes. QEMU can use it to understand what VMX capabilities are available, and so on. They are not yet implemented in QEMU and libvirt. Patches are on the list for QEMU. And the idea is that when all the work is done, QEMU and libvirt users shouldn't care if a feature bit comes from CPUID or from MSR. Almost. There is one particularly important MSR for speculative execution mitigations. It's called Arch Facilities. You discover it via CPUID, and then the extra information on speculation execution mitigation is available in this MSR. We added the support to KVM, not yet in QEMU. Patches are on the list. The problem with this MSR is that it includes what we could call both positive and negative features. So positive features means you are safe. Negative features means you are not safe. For example, the first one is a positive feature. It says that the processor is not vulnerable to Meltdown, which Intel called rogue data cache load. The second one is messy because it says always stuff the return buffer. It tells you always do this mitigation. What is the return buffer? The return stack buffer is basically a simple branch predictor for indirect branches, and it's specific to call and ret. But because a ret is effectively an indirect branch, on Skylake, Intel decided that empty return stack returns could actually fall back to the other branch predictor, the one that was vulnerable to Spectre and variant 2. The OS, in order to avoid that returns be vulnerable to Spectre variant 2 can do dummy calls at certain points. It will keep the RSB full, and because it's full, it doesn't fall back to the BTB, and it's not vulnerable to Spectre v2. The way to check whether you should do these dummy calls is to check the family model stepping, which of course doesn't work on virtual machines. So there is this bit that is called RSBA, and it indicates that the VM may run on a processor vulnerable to exploits of empty RSB conditions, regardless of the family model. So what's the difference between these features? RDCL no must be clear if the guest will ever migrate to an unfixed processor. Fine. Let it clear if you don't know that it exists, and the processor will just work a bit more slowly. But everything is just like any CPU ID bit. RSBA, you must set it if the guest will ever migrate to Skylake. I started this VM 1 year ago. How was I supposed to know that this bit even existed? It wasn't even in any manual. It wasn't defined. So please, Intel, we have this one, but do not define more negative features. So going quickly to the other ones, Chickenbits, typically they're set by the firmware, sometimes by the OS. In our case, we just set them in the hypervisor, nothing to do in the firmware. We just set the value, and the operating system reads it and sees that it's not vulnerable. What we do is that we provide the Chickenbits registers for any host or guest family model stepping. So far, we had no conflict between two different Chickenbits on different microarchitectures. So far, we are safe. But it can be a problem in the future. The last problem is the lack of PCID. What happens is that different features exist across low-end versus high-end platforms. So there's consumer and workstation platforms that Intel calls them, for example, Pentium Core and Xeon E3. Server platforms, instead it's Xeon E5 and E7, now Gold and Platinum, I think. It's hard to know exactly which features were in which processor. You actually have to find the processor and catch CPU info in that computer. And it's even harder to get it right if you don't have access to the processor because it's not released yet. As a result, some models in QEMU are wrong. What happens is that maybe some features migrated from low-end to high-end platforms, and it was added by mistake to the low-end platforms, or vice versa. For example, PCID was there in Nihalem server, but they added to some Westmere client. And then Westmere in QEMU doesn't have PCID. And despite actually the old Westmere processor having it, or almost always, I don't exactly know, because there's no comprehensive list. And the lack of this feature really went unnoticed until Meltdown, when people started noticing that everything was running like 5 times slower. So to sum up things, what makes CPU models hard? There's dozens of flags. They are interrelated. They are defined in a hard in the case of these vulnerability mitigations. And there are so many SKUs that it's hard to define what processor has which flags. In addition, sometimes we take backwards compatibility too seriously, probably, such as in the QEMU 64 default case. And there are some APIs and limitations in QMP that we have to fix in order to make CPU models more manageable by the user. So backwards compatibility means that libvirt wants to keep every past XML that has been used by a user runnable with the same guest ABI if you run it on the same guest. Not only the so-called persistent guest that you add to libvirt with virch define, but even if the user had XML on his disk and runs it with virch create, libvirt wants to keep it runnable with the same guest ABI forever. As a result, libvirt has PC machine type as a default rather than Q35, which is probably OK for now, but the problem is that it's very hard to change it in the future. And QM64 is already a problem now. Also, QMP has some limitations so that libvirt cannot really query CPU model changes across QEMU machine types. And if the CPU model changes, libvirt has a hard time defining runnability. And as a rule, we cannot change the runnability across machine types. And it's really hard to add new features provided by new kernels, such as, for example, new enlightenments, new virtualization features. And this is really the last slide. What we're planning to do is to add version CPU models, something like Haswell 3.1 for QEMU 3.1. It will also be accessible through Haswell, version equal 3.1. This way, libvirt can know about Haswell-3.1, but machine types know about the version property, and they can specify through a compat property. And if you have just minus CPU Haswell, the actual version will depend on the machine type. The good thing of this is that libvirt has a way to query it, and especially has a way to store it and preserve it across live migration. And finally, the open issues. One is there's no clear idea of what is the minimal required kernel version by QEMU, and no idea of how to change that. Currently for Intel, for example, is 3.6. But if we added nested virtualization by default, suddenly we would bump the minimal kernel version to 4.20. And this is hard to do upstream. In a downstream distribution, you have some control of what kernel is supposed to run on that distribution. But upstream maybe has people that are running ancient kernels on very new QEMU, and you cannot really change it. And another issue is the maximum physical address. It's not easily virtualizable and wildly different across processor queues. And this is something that has to be fixed in the hypervisor so that we can fix the skew problem, not just regarding the flags, but across all of CPU ID. And finally, CPU models in between QEMU and libvirt are basically have duplicated definitions. If we add the machine-specific, the version machine type-specific CPU models, the version CPU models is going to be even worse. So basically, this is the issue that has to be fixed before finishing the work on the version CPU models. There's not really time for questions, so let's.